All right, guys, we're going to continue with chapter 10 and 10.2, actually, which is graphing cubic functions. So here we go. So we graphed square root functions, and now we're graphing cubic functions. So a cube root function is just another type of function. You'll notice that it looks pretty similar to the square root function that we saw in the past. The square root function was just this one part, and then the cubic function has the second part that's in here. So a cube root just has that index value of 3. The domain and range for cube functions or cube root functions is all real numbers. So this is the parent function, which just looks like the cube root of x, which you can see right here. And we'll continue to look at transformations that are related to that. So here's graphing the cube root of x minus 4. And we want to compare that to the graph of just the cube root of x. So let's take a look at both of those graphs. So you can see, just like we've seen in the past, and again, we're using Desmos to graph these, and I'll show you at the end how to go about doing it as Desmos. But we notice that minus 4 is on the outside of our graph. So those rules that we have with translations that you saw in the last lesson that hopefully you've written down hold true again here. So we've got that minus 4 on the outside of the cube root, which means that this is a vertical translation or a vertical shift down 4 units. So it's important that you know the vocabulary that goes along with these things, because frequently you're going to be asked to compare a function to the parent function there. And again, you can use technology, Desmos, and then if we were in the classroom, a graphing calculator to actually graph that function. But you want to know that basic shape of a cube root function. If we take a look at all of these, obviously here we've got plus 3 on the outside, so that would be a vertical shift up 3 units. And then, for whatever reason, the graphs aren't showing up. But if we looked at what each of these would be, when we have an inside underneath the square root, it moves in the opposite direction that we would think horizontally. So this would be a horizontal shift to the right 5. Actually, this would be a good time to show you on Desmos how to go about doing this. So if we exit here for a second and we go to Desmos, we'll see how to go about taking a look at the translation that's been made. So I'm going to start by graphing the parent function. So in order to do that, I've got to go to my keyboard. You'll notice that there's no cube root that pops up. So in order to get the cube root, that's a square root. That's not going to help. We have to click the functions key, and we have to go to miscellaneous. It'll probably start on trig, but if you go to miscellaneous, and then you see right here, this is a cube root, or how you can get like a 4th root, a 5th root, any of those roots. So we're going to click that one. And then we can put our index, which is a 3, and an x, and there's our parent function right there. Now, if we want to see our new function, we would go ahead, same thing. Oops. I'll go to my second line. Cube root, and now we have x minus 5. So you can see we have the exact same graph, but we've just shifted our graph over 5 units, all right? Which we can see right here. The last example in this particular set had a 4 on the outside of it. So we should be thinking a 4 on the outside is going to make a vertical stretch. So let's put that 4 on the outside. Then go to our functions key. And then an x. And you can see what we've had here is we have a stretch of our function. We can see that it's stretched upward. So that would be a vertical stretch by a factor of 4. And again, we could write that in as well. And here are the graphs. There's our horizontal shift, and there's our vertical stretch by a factor of 4. So let's write that in. Oops. And it's a stretch because we've kind of expanded. All right? And again, we've seen on Desmos how you can go about graphing them. Let's keep going here, okay? Example number 2, we want to see what's going on here. So let's get rid of this. And we can see that there's 2 things that are happening here, okay? And let's highlight both of those things that are happening. We've got that negative on the outside, and then we've got that +2 on the inside here. So if we realize what that negative does, that negative makes a reflection. So we have a reflection, and our reflection is in the x-axis. Okay, it flipped across the x-axis here. We can see our graph, if we look between the red and the blue on the right-hand side, we have a flip over the x-axis. So we have a reflection in the x-axis, and then we have that +2, which means we have a horizontal shift to the left too. So you can see the key thing here is knowing what each element of the cube root, how it's affecting in terms of the parent function. A lot going on this one. So we've got a bunch of things happening here. And again, you want to go step by step. You want to go, what is the 2 doing? What is the -3 on the underneath the square root doing? What is the +4 doing? So let's start with the -3. Actually, we'll just go step by step. Let's start with the 2. The 2 is going to cause a vertical stretch. So we have a vertical stretch by a factor of 2. Let's look at the -3 underneath. Underneath the square root moves left and right. So that's going to be right 3. And then that +4 on the end is going to be up 4. So this is a horizontal shift or translation to the right 3. And then this is a vertical shift or translation up 4. All right, if we look at the graph, won't go away. But if we look at the graph, it would be doing all of those things there. Okay, same idea on this one. I don't think we need to go through these examples. You can see all the different graphs and what they're doing. Okay, this is vertical stretch, right 1. Here, a little bit confusing because we have a negative x in there, but the same idea holds true. The graph of the cube root function m is shown. Compare the average rate of change, where we have the cube root of 1/4 x of change from the interval from 0 to 8. So we're looking from the interval from 0 to 8. So from here, let me get my pen out. So from 0, doesn't want to click on there. Oh, here we go. So from 0 to 8 in the x values. So when we see average rate of change, what we're talking about is we're talking about the change in y. So delta y over delta x. So in essence, that means y2 minus y1 over x2 minus x1. So if we look at our points here, we have a point at 8, 8. That'll be my x2 and my y2. And we have a point at 0, 0. So to find our average rate of change, we're going to do 0, 0, not 0, 8. We're going to do 8 minus 0 over 8 minus 0. So our average rate of change is just 8 over 8, which is just equal to 1. So this is not linear, okay? But the average rate of change is 1, meaning it is going up on average. For every additional x, it's going up 1 y value. But it's not a constant rate of change, okay? That's the average rate of change. We're going to hold off and not go through the word problem here. You can take a look at that on your own. It says use a graphing calculator to graph the function. Obviously, we would be using Desmos to graph this function. And we want to use it to estimate the age of an elephant whose shoulder height is 200 centimeters. So let's actually take a look at that. Let me get out of this. This will be a good use of Desmos again. We've got 62.5 cube root of, we'll use x plus 75.8. So we've got 62.5, and then I have to go to put my cube root in. The cube root of x. And then the rest was plus 75.8. Now, what this is asking me, if we zoom out, we're going to have to zoom out a lot. There's my cube root function. You can see it looks like all the ones that we've seen in the past. It's saying estimate the age of an elephant whose shoulder height is 200 centimeters. So we're looking at the shoulder height, and shoulder height represents my y value here. So I have to find a y value of 200. Okay. When I look at a y value of 200, I can see that by looking at my graph, it looks like at 8, we have 200.8. So it looks like it's roughly or about 8. And our t represents the age, so 8 years old. So it's approximately 8 years old to have a elephant whose shoulder height is 200 centimeters. All right, and again, we can just use Desmos to find that value there and look at the graph. So key thing here is make sure that you know all of your translations. Okay, make sure you know what the inside underneath the square root is doing. Make sure you know what the outside is doing. So just to kind of recap, when you have a number on the outside, that's your vertical stretch and vertical compression. Inside underneath the square root over here, that moves your left, right in the opposite direction that you would see. On the outside, like we see right here, that moves up and down. You'll notice right here, we have a number in front of the x. That's a vertical reflection, or a reflection over the y-axis. So that's what that value does here. So this is a horizontal over the reflection over the x-axis, and this is a reflection over the y-axis. That's it. Make sure you know the shapes of the cube roots and make sure you know how everything moves, and you should be good to go on this lesson. Good luck, guys.